Hi, welcome to solveandgo.com. Today we're going to do a related rates problem. This will be the first related rates problem we'll do. It involves distance. So distance is changing. Let me post up the problem for you. So here we have, at noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between them changing at 4 p.m.? Okay, so pause the video and copy that down. And let's first draw a diagram. This is pretty much always the first step to approaching a related rates problem. Okay, drawing some diagram. Okay, well, let's take the top of the page to be north. And let's see what's happening at noon. So we start, and ship A is 150 kilometers west of ship B. Okay, so the distance between them at noon is 150 kilometers. We know ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. Now let's see what's happening at general time t in the future. So at time t is in hours in this problem. So what we have here is the original, I'll mark this in purple, is the original position of ship B. Okay, so in relation to that, ship A is, say, a little closer here, and ship B has sailed north. Okay, this is ship A, and this is now ship B. How, in relation to ship B's original position, what's the length, what's the distance between ship A and ship B's original position? Well, it was 150 kilometers away, but now it's closer by 35 t, because at time t, ship A has sailed east 35 times t, which is rate times time, kilometers. Okay, and what's the other side of what will be a triangle? How far has ship B sailed north? Well, this is 25 t. Okay, rate times time. Now the distance between them is the hypotenuse of this right angle triangle. And what will this be? Well, according to Pythagorean's theorem, this is d at time t is going to be the square root of 150 minus 35t squared plus 25t squared. Okay, so that's the distance between them at time t. Okay, so let's write that function up again. We have d at time t is the square root, I'll write it at the top of the page here, 150 minus 35t squared plus 25t squared. Okay. I'm going to expand this bracket here in under the square root sign. Simplify the expression a little bit. So what we end up getting is 22500 minus 10,500t plus 1225t squared plus 625t squared. Okay, all under a square root sign. And then simplifying it a little further by combining the t squared terms, what we get is 22500 minus 10,500t plus 1850 t squared. Okay, so now we want the rate that this distance is changing at time t, so we're going to take the derivative. What we get, we're going to have to use the chain rule, is 1/2. So this is the square root is taking the exponent to 1/2. So this is 1/2 22500 minus, okay, so I'm just putting what's under the square root sign here. Okay, and this is all to the power of negative 1/2. Okay, let me make that exponent a little bit clearer. Negative 1/2 is the exponent here. Okay, I couldn't quite fit it in, but you can see that the exponent's negative 1/2. And then we need to multiply this by the derivative of the function inside the brackets, which is going to be negative 10,500 plus 3,700 t. Okay, the derivative of 1850 t squared. Okay, so we're going to evaluate this function at t equals 4 hours later. So evaluate, spell it right, at t equals 4. Okay, 4 p.m. is 4 hours after noon. Okay, let me erase what's on top here. Okay, we're going to plug the values in. And what you end up getting is, so d prime at time 4 ends up being, so I'm going to do these calculations for you for the most part, 22,500 minus 42,000 plus 29,600 to the power of negative 1/2. And all of this is times 4,300. And the answer you end up with is 21.4. Okay, approximately kilometers per hour. Okay, and this, if you look back at the picture, this sort of makes sense. It's about the right value. How do we know that? Well, where exactly is the position of A at t equals 4? Well, it sailed east four times 35, which is 140 kilometers. Okay, so remember, d prime at 4, we said was, well, we calculated was 21.4 kilometers per hour. Let's look back at the picture. They were originally 150 kilometers apart. So again, if I let this purple dot here be the original distance, the original position of ship B. Okay, so ship B is somewhere up here. In fact, it's 100 kilometers up here. But important thing is ship A is very close to where ship B started, so 10 kilometers away. It's sailed. They were 150 apart, right? Ship A's original position here was 150 kilometers away from this purple dot, and now it's very close, which means that the distance, so that the rate that they're traveling apart should be approximately the same as ship B's rate, which is 25 kilometers per hour. Okay? Because ship A is very close to where ship B started, and ship B is moving away at 25 kilometers an hour from where it started. Okay? So that means the distance, the rate at the distance between them is changing, should be approximately 25 kilometers per hour, and 21.4 is close. Okay? So this kind of validates the answer that we got.